Hello. Today I'll be presenting a summary of the paper Adaptive Scalar Quantization with Outside Information by Antonio Ortega and Martin Vetterli. The core problem addressed in this paper is that standard optimal quantizers, like the Lloyd-Max quantizer, are typically designed for sources with known and fixed statistics. However, in the real world, many signals, such as images, have statistics that are either unknown beforehand or change dynamically over time. Using a fixed quantizer on such sources can lead to a significant drop in performance. The paper's goal is to propose a method for adaptive scalar quantization that can adjust these changing source statistics without needing to send any extra information, which is known as side information, from the encoder to the decoder. Because the adaptation relies on information available at both ends, it's called backwards adaptation. This slide illustrates why adaptation is crucial. A fixed quantizer like the LMQ is only optimal when the source matches the statistics it's designed for. When the source statistics don't match, a problem we call mismatch, the performance degrades severely. We can see this clearly from some tests conducted based on the methods described in the paper. Let's look at test 1, mean mismatch, which simulates figure 6.8 in the paper. An LMQ designed for a zero mean Gaussian source performs well at zero mean, but it plummets near 0 dB when the mean shifts from -2 to +2. In contrast, the proposed adaptive quantizer maintains its performance relatively consistently, staying above 7 dB across the average test range of means. This confirms the paper's claims that the adaptive quantizer maintains its performance constant against mean shifts. Similarly, in test 2, variance mismatch, an LMQ designed for unit variance sees its performance drop significantly as the source variance moves away from 1. The adaptive quantizer is again much more robust, staying above 7 dB across the range of variance tested, clearly outperforming the fixed LMQ in mismatch conditions. The key insights of this algorithm is that since both the encoder and decoder have access to the same sequence of previously quantized samples, they can both adapt their quantizers in the same way without needing any side information to be sent. The paper explicitly separates the adaptive algorithm into two main building blocks. First, source modeling. This block takes a history of the past quantized samples and uses it to estimate the source's probability density function. The algorithm assumes that the source's PDF is smooth and changes slowly over time. Second is quantizer design. Based on the estimated PDF provided by the first block, this part designs a new optimal quantizer, determining the updated decision boundaries and reconstruction levels. Standard techniques such as the Lloyd-Max algorithm can be applied here, but operating on the estimated PDF. This explicit separation allows us to use well-known quantizer design methods while focusing research on the source modeling changing based on the quantized data. For PDF estimation, the algorithm uses the counts of how many past quantized samples fell in each quantization bin over a certain memory window. It then constructs a non-parametric piecewise linear approximation of the source's PDF based on these counts and the current bin boundaries. Key challenges addressed here include the zero frequency problem, where a bin might have zero counts. To handle this, the algorithm adds one count to all bins. Techniques are also included for estimating the dynamic range of the source distribution, particularly for outer bins. The sources describe a sample, non-iterative approach that uses the bin's centers as knots for piecewise linear fit and solves a system of equations based on the probability mass observed in each bin to find the PDF value of these knots. For quantizer design, the algorithm applies the Lloyd-Max iterative procedure, but it uses the estimated piecewise linear PDF instead of the true one. it calculates the optimal reconstruction levels for the centroids of the estimated PDF within each bin and the optimal decision boundaries as midpoints between these levels. After designing the new quantizer with its new boundaries, a crucial step is to update the internal bin counts to reflect these new boundaries, maintaining a running memory across updates. This update involves rounding the current bin count based on the overlap ratio between the old and the new bin intervals. This paper also discusses determining the speed of adaptation or the memory length, noting the trade-off between having enough data for reliable estimation and being able to track rapid changing statistics. Using a forget factor or threshold short-term versus long-term counts are mentioned as approaches. The paper analyzes the performance of these adaptive approaches. For stationary sources, when the statistics don't change, there is a small performance loss compared to a fixed LMQ designed optimally for that source. The paper's table 1 indicate this loss is minimal, less than 0.1 dB when optimally initialized. Our test 3 comparison shows a large difference. The LMQ trained on the full Gaussian sequence achieved 9.37 dB average SNR, while the adaptive quantizer initialized from scratch achieved 7.36 dB. This difference likely reflects the adaptive quantizer's startup phase and the effect of the finite sequence length used in the test. However, the strength of the adaptive algorithm lies in handling time varying on non-stationary sources. For sources with changing behaviors like a bimodal source that switches between different means, the adaptive algorithm is expected to outperform the LMQ design based on the overall long-term statistics. While our test 3 shows the LMQ trained on entire bimodal sequences had a higher overall average SNR of 8.37 versus 6.67. The paper figure 7a, which is our test, also generated figures for, illustrates that the adaptive quantizer performs better on a block-by-block basis as the source characteristics change, demonstrating its ability to track local statistics more effectively than a static LMQ. This method is applicable to scalar quantization in general. It can be used within a DPCM loop or with advanced schemes like trellis-coded quantization or scalar vector quantization that build upon scalar quantizers. It shows promise for applications such as image compression, for instance, in quantization subband coefficients. In summary, the paper introduces a backward adaptive scalar quantization technique. A key feature is that it requires no cited information by adapting based purely on past quantized samples. The algorithm is conceptually separated into two main parts: source modeling to estimate the PDF from quantized data, and quantizer design using standard methods like LMQ on the estimated PDF. This approach is robust to mismatch in source statistics, such as changes in mean or variance, where fixed LMQ performance degrades significantly, and other performance advantages for non-stationary sources by tracking local statistics better than source quantizers, while introducing a small loss for purely stationary sources compared to theoretical optimum. This loss is shown to be minimal in typical cases. Key technical elements include using piecewise linear PDF approximations based on bin counts, managing issues like the zero frequency problem, and estimating the dynamic range. For future work, the author suggested extending the ideas to vector quantization, further exploring its suitability for DPCM applications, and refining techniques for dynamic range estimation and controlling the adaptation speed. Finally, I implemented the code on my own to recreate the tests that they have mentioned. I was able to recreate figures 6A, 6B, and 7B the same as what they had stated in their work. Figure 7A is slightly different, showing the opposite showing the opposite trend that they stated, where the adaptive is actually worse than the Lloyd max.